Hi, this is your teacher Barbara Rademacher, and we're going to do a linear programming problem. This is the real deal. This is how math is really used in real life. Carlo and Anita make mailboxes and toys in their craft shop near Lincoln. Each mailbox requires 1 hour work from Carlo and 2 hours from Anita. Each toy requires 1 hour from Carlo and 1 hour from Anita. Carlo cannot work more than 7 hours per week, and Anita cannot work more than 10 hours per week. If each mailbox sells for $8 and each toy sells for $25, then how many of each should they make to maximize their revenue? Well, that's a complicated problem because it's a real life problem. And you should probably read this several times and then gather all of your information, which I've done right here. Incidentally, the objective function is whatever it is you're going to maximize or minimize. Do you recall when we worked on quadratics? We did quite a few maximization or minimization problems. But this isn't quadratic. These are straight lines. We have to use a different method for that called linear programming. So here are some of the facts that we've gleaned. To make a mailbox, Carlo works 1 hour and Anita works 2 hours. Now, they're going to make more than one, so let's let X equal the total number of mailboxes made in a week. Well, Carlo then will make 1x or X, or will use 1x hours on the total number of mailboxes used. That is 1 hour per mailbox times the total number of mailboxes. Anita will use twice that many. She'll use 2 hours per mailbox times the total number of mailboxes made. Over on the toys, each toy takes Carlo 1 hour and Anita 1 hour. If Y equals the total number of toys made, then Carlo puts 1 hour per toy times the total number of toys into the total number of toys, and Anita puts 1 hour per toy times the total number of toys in, the exact same time as Carlo. Okay, our constraints in life you have constraints. Our constraints are that Carlo, not Carol, Carlo cannot work more than 7 hours, and Anita cannot work more than 10 hours. And there's also an implied constraint, namely that Carlo and Anita are definitely not going to work a negative number of hours. What would that be? I don't know. So 0 is as low as either of them can go. That's called an implied constraint. All right, so if we look at Carlo's total number of hours working per week, we see that this inequality would state Carlo's number of hours working. X number of hours on the mailboxes and Y number of hours on the toys, but he cannot work more than 7 hours. He can work 7 hours, but not 7.5 hours, okay? Anita, her total number of hours spent working on mailboxes and toys is 2x plus y, but she cannot work more than 10 hours. She can work 10 hours, but not more. All right, now what are we going to do? We're going to graph the constraints, including the implied constraints. The implied constraints are that x is greater than 0 and y is greater than 0. So that means we're working in the first quadrant of the Cartesian plane, okay? This is where reality takes place most of the time. What we're going to do to maximize the objective function, which is the revenue equals 8x plus 25y, because x is the total number of mailboxes, and they sell for $8 each, and y is the total number of toys, and they sell for $25 each. So this is our total revenue income function. The vertices are very important in linear programming because we don't have the turnaround point that a quadratic would have. Instead, we have to use these turnaround points: 0, 0, 0, 7, 3, 4, and 5, 0. These are the vertices that enclose the shaded area that is the solution set for our inequality, for our linear programming problem. All right, now, this is obvious. These are the actual x-intercepts and y-intercepts of some of the graphs. This is the y-intercept of the green line, which is Carlos' work, Carlos' constraints. And this is the x-intercept of Anita's constraints. And 0, 0 is clearly the termination point of the graph, if you will. So those are easy. How do you come up with 3, 4? Well, you solve the system. 3, 4 is the intersection point between the green line and the blue line. So take those two equations and solve them as a system. You can use substitution elimination, also called addition, or the matrix method, all of which I know you know by now. So what we do is we take each vertex, we take the x-coordinate of each vertex and put them in for the x, substitute them for the x in the objective equation, and we take the y-coordinate and substitute it in the y for the constraints, which is up here, and which I should have copied down there. I now realize that. So here we'll have the total when we substitute the x-coordinate and the y-coordinate. We'll have 175 for the 0.07. We'll have 40 for the 0.50. We'll have 0 for the 0.00. And we'll have 124 for the 0.34. Well, obviously 175 is the largest of the four numbers. 175 is the maximum revenue, the most that this company can make in a week, if they don't build any mailboxes and if they stick to toys. So we now know that the way to maximize their revenue is to make no mailboxes and make 7 toys. All of the other mixtures, that is 5 mailboxes, no toys, no mailboxes and no toys, and 3 mailboxes and 4 toys. All of these will bring in different amounts of money. That will bring in 0, but 175 is the largest. So this point, this vertex, 0,7, will maximize the revenue. Okay? All right. Talk to you later.